about quantum physics and about recent developments in quantum science, which promise to may have in the future applications for innovation and technology. As you know, quantum physics has opened to us the microscopic world. It has given us the explanation of phenomena at the atomic scale. And at the same time, from this understanding, it has given us also the keys of all modern technologies. What is paradoxical about quantum science is that it's a very powerful theory, but at the same time, it's a rather strange theory because the laws which rule the world at the micro level are very counterintuitive. Systems behave according to what is known as the superposition principle or involve a phenomenon called entanglement, and all this is illustrated by the famous metaphor of Schrödinger, the Schrödinger cat paradox, and it leads to phenomena which are very difficult to understand if you are a classical physicist. In fact, the American physicist Richard Feynman used to say that nobody understands quantum physics, and of course you have to take that with a grain of salt. It means that you don't understand intuitively what quantum physics is about because we are used to think into classical terms. The world around us behave according to classical physics, and the quantumness is usually veiled at the macroscopic level. Nevertheless, recent experiments in which we are now able to manipulate individual quantum systems allow us to observe directly this quantum strangeness, and let us hope that one day we could harness this strangeness to perform and to build new devices for communication, computing, or precise measurements. And I would like to talk to you about that today. But before I do that, I want to remind you that quantum physics is essential to understand the world. Quantum physics is invoked to understand the structure of atoms, for instance, how electrons behave inside atomic system. It's also very important to understand how atoms bind with each other, that is, to understand the structure of molecules and the whole field of chemistry. And even at the macroscopic scale, in systems which are made of billions and billions of atoms, some properties, like, for instance, superconductivity, cannot be understood without invoking quantum laws. And for instance, in superconductor, magnetic fields are expelled from the superconductor, and this leads to this levitation experiments that you can see on the screen. Even at the cosmic scale, quantum physics is important. You see on the last picture here, the very tiny fluctuation of the intensity of the cosmic radiation background, which originated something like 300,000 years after the Big Bang. And the tiny fluctuations that you can see on this picture in false colors are due to quantum fluctuations which occurred in the early universe. And these fluctuations are essential to understand the formation of galaxies, for instance. So you see that quantum physics is a theory which explains phenomena at all scales. It gives us a deep understanding about nature, but at the same time, it has given us the tools of modern technologies. For instance, computers are based on the combination of very small transistors which obey to quantum rules, so you need quantum physics to understand the behavior of ordinary computers. You need also quantum physics to build lasers. Lasers exploit the interaction of atoms with photons at the microscopic scale, and you need quantum physics to build lasers and to understand their behavior. Atomic clocks are also, of course, systems that could be invented only from the knowledge of quantum laws. The atomic clocks are counting the transition frequencies in atoms, which are very stable, and very precise clocks can be built on that. And for instance, the GPS system, which is based on clocks which are orbiting the Earth in satellites, are based on this understanding of this quantum phenomenon. And you know that the GPS allows us to position ourselves by just receiving signals from these atomic clocks with a very high precision. The last example I give you here is MRI scanners. Magnetic resonance is a quantum phenomenon, and we have inside our body very small magnets in the nuclei of our atoms, especially of water molecules, and these nuclei emit radio waves which are detected and which are transformed into very precise images, which are very important for medical diagnosis and also for research. And all this is possible only because we have a deep understanding of the microscopic world and of quantum laws. So, but what I want also to stress is that this quantum era has started at the beginning of the 20th century by the discovery of quantum physics. And physicists who lived before that, before the quantum age, were absolutely unable to predict what was going to happen. Lord Kelvin was the Pope of physics in 1900, and he said that physics was almost achieved and nothing new was going to happen. And at that time, at the beginning of the 20th century, people were trying to find out, to imagine how physics and how innovation would make the 20th century different. And so they imagined this kind, there are some postcards which were published at that time that you can see here, and we give a very naive view of what the world should be in the year 2000. They thought that transportation would be made by balloons and that there would be some kind of hybrids between trains and boats, and this kind of thing were just extrapolation of classical physics, but of course they could not imagine the computer, the cell phone, the lasers, and so on. So this should make us very careful if we want to predict what would be science and physics in 100 years from now. Why is quantum physics so different and so disruptive as compared to classical physics? Where is the strangeness of the quantum coming from? It resides into the principle of quantum physics. One of them is the superposition principle, and I will give more details about that later on, which tells us that the system, a quantum system, can be in different classical states at once. Another word that you might have heard of is entanglement, the fact that two systems which are separated in space can still speak to each other, have some kind of immaterial link between them, which is very strange according to classical physics. These concepts are illustrated in the famous tale of the Schrödinger's cat, as I will tell you in a moment. As I said already, this strange logic, which is at work at the microscopic scale, is usually veiled when you look at large systems, and it is why the large macroscopic world appears to us to be classical. The only way to observe this strangeness is to be able to manipulate isolated quantum systems, single atoms, single photons, or small collection of this system in a very controlled way. And these are kind of experiments that we are now able to perform in the laboratory, and they give us, as I said, some hope that we will be able one day to exploit directly this strange quantum logic for practical applications. So let's try to illustrate the strangeness of quantum physics by describing a very simple experiment that you all physicists have heard about, which is an interference experiment, the Young double-slit experiment that have sketched on the screen. You have a source of light or a source of particle that you can see on the left part of this slide, and the particle or the light is crossing a screen which has two slits or two holes in each, and then the particles are collected on a second screen, and you see a pattern of bright and dark fringes appearing on the screen. This is easy to understand if you assume that the system that you are looking at is a wave. The wave is arriving on the two slits, and then you have two wavelets which are emerging from the two slits, and these wavelets interfere, and there are some direction in which the two waves add up, and it gives bright fringes, and other direction in which they subtract, and this corresponds to dark fringes. And this wave description is precisely the one which was invoked at the beginning of the 19th century to find out that the light was a wave, that light, and then it was understood later on that it was in fact an electromagnetic wave. But the same experiment can be achieved with very faint light sources up to the point where single particles of light, single photons, are crossing the apparatus one by one. And the question is, what happens if you build up these interference fringes photon by photon? And in fact, I will show you here on the right part of the slide, a real experiment in which the source is very weak and one photon at a time is crossing the apparatus. And you will see how the fringe is built up with this movie. What you see is that each photon is striking the screen at a point. So the photons arriving one by one seem to tell us that they are particles. But then when enough particles have reached the screen, you see that a wave pattern is emerging. You start seeing the dark and the bright fringes. But the question, which is impossible to answer by a classical analysis, by a classical mind, is how does a single particle, a single photon, decide, for instance, that it will never arrive on a dark fringe? If you are discussing classically, the photon should cross the system through one fringe or the other. This is a classical description. And then it doesn't make any difference whether the other one is open or closed. So in fact, photons arriving one by one should arrive anywhere and do not give this pattern. So if you think about that, the only interpretation that quantum physics tells us is that each photon must pass through both holes at once, and this makes no sense. This means that classical trajectories are no longer meaningful at the quantum level, and it leads to the superposition principle. Quantum physicists tell us that, in fact, what happens is that the state of the system is now in a superposition of a state in which the particle is crossing through one slit and the particle crossing through the other slit. And the same dilemma occurs for matter. You can do the same experiment with electrons, with atoms, with molecules, and you find the same result, the fact that the particles have to be in a superposition of crossing through the two slits. This is the superposition principle, and it leads to the picture of the Schrödinger's cat, as I will tell you in a moment. So in fact, quantum physics is based on this wave-particle duality and on the superposition principle. Einstein found out in 1905 that light, which is a wave according to classical physics, is also made of discrete particles. And about 20 years later, the French physicist Louis de Broglie said that material particles, such as electrons and atoms, also can behave as waves. I can, in fact, give you a picture to try to make you feel what it means. You see this ambigram here can be read either as light is a wave or light is a particle, depending upon your state of mind. So, but of course, in quantum physics, it's not your state of mind which matters. In fact, what matters, according to Niels Bohr, is the kind of apparatus you are using. Which aspect of reality is observed depends on the experimental setup. When you couple your system to observe the system with an apparatus, this apparatus will perturb the system in a way which will make it behave either as a wave or as a particle. This is called Bohr's complementarity, and it looks very strange for classical physicists, of course, and Bohr, which likes to make some ambiguous statements and jokes, used to say, if you are not shocked by quantum physics, this means that you have not understood it. So it's, in fact, it's really shocking because we are not used at the macroscopic level to these strange laws. In fact, at that time, at the time when these quantum theories were elaborated, back in the 1920s, the founding fathers of quantum physics, people like Einstein, Bohr, Schrödinger, used to imagine experiments in which the quantum principle would be displayed in simple terms. These experiments were at that time impossible to perform because of technological shortcomings, but now they have become possible. And I describe you here one of these experiments. In fact, Einstein did not like this complementarity view, and he tried to imagine an experiment in which one would be able, inside the interferometer, to find out what was the trajectory of the particle. So the setup that he imagined is shown on the left part of this slide. It makes a very slight modification to the Young double slit. He just assumed that the upper slit was movable, that it could go up and down. It was just held by springs. And his idea was the following. He said, if you want to find the trajectory, you just have to find out whether the upper slit is moving or not. If the particle is going through the upper slit, it will be scattered off the edge of the slit, and the slit will start going up and down. And if the slit moves, it means that the particle went through this slit. And so the question was, will you see the interference in that case? Will it violate complementarity? But Bohr did not take too much time to find where was the flaw in this argument. He said, if you want to use the slit as an apparatus to detect the passing of the particle, the uncertainty on the momentum of that slit should be very small, because the change in momentum due to the scattering by a particle will be very small. So delta P, the uncertainty on the momentum should be small. But then, according to quantum physics, delta X, which is the uncertainty on the position of the slit, should be large, because the product of these uncertainties has to be larger than H, which is Planck's constant. This is a well-known Heisenberg uncertainty relation, which is at the heart of quantum physics. And so if delta X is large, it means that the difference of passes in the interferometer will be blurred and the fringes will disappear. So Bohr was able, by this simple argument, to show to Einstein that within the principle of quantum physics, there was something which forbade the simultaneous observation of the particle and of the wave aspects. I think what is also interesting in this picture is that the concept of entanglement is already here. You see, I am showing you here that the state of the particle in the interferometer is a superposition state. Either the particle is crossing either through the lower slit or through the upper slit. And in fact, the particle, for interference to be observed, have to be in a superposition. But the particle is not alone in this story. You have also the slit itself, and you see that if the particle crosses through the upper slit moves, and if the particle crosses through the lower slit, the upper slit doesn't move. And so the state of the particle plus the slit is now an entangled state. You don't have any quantum state anymore for the particle alone, for the slit alone. You only have a combined quantum state for the two, which is not separable. And this is a definition of entanglement. In fact, this experiment has also in it the germs of the Schrödinger cat. You see that the slit, which is a large object, gets entangled with the particle, and the slit is now in a superposition of moving and not moving at the same time, which is, of course, impossible for a classical particle. In fact, Schrödinger gave a much more dramatic twist to this situation by imagining that you have in a box a living animal, let's say a cat, and that the cat is interacting with a single atom. This atom is in the upper right part of the box, and the atom evolves into a superposition of two quantum states. The atom is either excited and nothing happens, or it decays to a lower state and emits a particle which triggers a device which would kill the cat. And since the atom is a quantum object, the atom can be in a superposition of being excited and not excited, which means that the cat should be in a superposition of being dead and alive. This is exactly the same argument as the one that I gave you on the previous slide, but now, of course, it becomes much more dramatic because the fate of a cat is much more interesting for us than the fate of a slit in an interferometer, but it's exactly the same picture. And you see that this story tells us that as soon as, if you can make a small system like an atom interact with a large system, then the quantumness is translated from the microscale into the macroscopic scale. And this leads, of course, to absurd results because nobody ever observed a cat being at the same time dead and alive, and it even does not have any meaning classically. So it immediately raises the question of the transition between the quantum world and the classical world. Why, when you increase the size of systems, this oddness, this strangeness of the quantum world disappear, is veiled, and this is a problem of decoherence that I will address in just a moment. So to summarize the strangeness of quantum physics, what can we say? Suppose that the particle is crossing a system which has two slits, as I said before. Classically, you see here, you seem to see two particles, but in fact, I don't know how to show it in classical terms. It's just one particle which is at the same time at the left and at the right, and I have tried to write it in a symbolic way, in this way. So a particle can be at the same time in two different positions, but also you have other kind of superposition. For example, an atom which has different energy levels can be at the same time in one energy state in another state. And one way to achieve that is to apply a pulse of light which connects the two states. And if you apply a pulse of light which has the right duration and the right amplitude, you can prepare a superposition of these two energy states, which I write in this way. You see the system, the electron is occupying either one orbit or the other. In fact, it occupies both orbits at the same time, and this is a superposition state 2. Now, these state superpositions are very fragile. If you try to measure them, to observe them, then the superposition will collapse. And this is the principle of measurement in quantum physics. If you try to measure a system, you will perturb it. For instance, if you want to find out whether the particle passes through one slit or the other, of course you have to shine light on them just to see. And the light carries momentum, and as the light is scattered on the object, it will perturb the position of the object. It's what I have tried to symbolize here. A very simple measurement apparatus is just a beam of light and your eye which detects where the light has been scattered. But if you do that, you perturb the system and you destroy the superposition. And what you find out that the atom is either on the right or on the left, and this occurs randomly. In a random way, you have a 1/2 probability to find the particle at left and at right. And as soon as you have done that, the superposition is destroyed and you can no longer see any interferences. This randomness was such that Einstein used to say that in quantum physics, God is playing dice. God is playing a random game. He did not like that idea, but all experiments in quantum physics show that there is, as soon as you perform a measurement, the result is random and you can only predict the probability of the different outcomes. Now, a few words about decoherence. What happens if you look at a large system? Let's take again our interference game and suppose now that we are doing it with large balls, billiard balls, for instance. Why don't we see interferences in this case? Nobody has seen a billiard ball going through two holes at the same time. What happens, according to the decoherence theory, is that a large object is always coupled to an environment. For instance, you have air molecules, black body photons surrounding the balls, and you get very quickly an entanglement between your large system and the environment. In the case of a cat, just to have a cat living in the first place, the cat has to interact with a lot of molecules. It cannot be frozen to death at very low temperatures, so you have black body photons around. And this creates entanglement with the environment, and you can look at the environment as a kind of measuring device which all the time is spying upon the system and forcing it to choose one of the two classical outcomes, here or there. So to make it short, the environment performs a kind of measurement which destroys the superposition in large systems, which explains why the macroscopic world appears classical and why you don't see interferences between dead and live cats. A few words about another phenomenon that you can have heard of is entanglement and what you can do with entanglement. What I have shown here are two particles. Each of these particles can have two quantum states, which I have symbolized in red and in blue, and which can also be called 0 and 1. And when you have a two-state system, you can always consider that the system is storing a bit of information, which can take two values, 0 and 1. And I assume that these two bits are entangled. What it means is that if the left bit is a 0, the right bit will also be a 0. And if left bit is a 1, the right bit also will be a 1. And if you make a measurement on the left bit and find 0 or 1, you find it randomly, but immediately the other bit will have to assume the same value. So this is entanglement. And the property of entanglement is that it survives separation. If the two bits are entangled, and if they travel over a very large distance, they remain entangled. This experiment has been performed with photons. You entangle two photons, and then you send them on two fibers at hundreds of kilometers from each other. if you perform a measurement on the first photon, for instance, look at this polarization, you find 0 or 1, and immediately the other one has to assume the same value. So it is as if two dices which are cast at large distances give random results, but always correlated random result. This is this is called non-local randomness. And this non-local randomness is very strange. It's a quantum property. And it is now being used to share between partners which are at large distances, random keys, random sequences of 0 and 1s. And one of the partners can use his random key to just to code a message, to encode a message, and to transform a message into a kind of random succession of 0 and 1. And this message can only be deciphered by the other partner if he has the same key. And one way to share the key is to use entanglement. And if you use entanglement to share the key, nobody can spy upon the keys, because if you try to spy, you will perturb the system, destroy the randomness, and the partners will be able to know that they have been spied upon. So this is the basis of quantum cryptography, which is now being developed in many labs in the world. This quantum cryptography requires still a lot of research, because you have to be able to keep this quantumness over a long time. So you have to fight decoherence, you have to realize some quantum repeaters would allow you to propagate this entanglement over large distances, and you have to also to increase the bit rate to make it useful. So there is still a lot of research going on. But what I want to reflect upon is just to understand why these thought experiments are now becoming possible. And in fact, they are becoming possible because technology has evolved since the time of the founding fathers of quantum physics. We have new tools which allow us now to probe and to manipulate single quantum particles. First of all, lasers have known a tremendous development over the last half century, and you need lasers to prepare atoms in very defined quantum states. And the second development, which is very important, is the development of computers. You need fast computers to process a very large amount of data in real time and to get all this information from the atoms in real time. In some experiments, like the one we are doing in Paris, you also need very good superconducting materials to prepare and to get very good mirrors which reflect light without losses. What I want to stress is that these technological advances are coming from quantum physics. Lasers, computers, that is transistors, superconductivity is a quantum property. So you see that we have here a kind of virtuous circle. Theory has allowed us to develop technology, which in turn helps us to improve our understanding and our probing of the microscopic world. So let's say a few words about the quantum, the Nobel Prize in 2012, which I have shared with my colleague and friend Dave Wineland, who is working in Boulder. The quotation is for the control of quantum particles at the quantum level. And in fact, the experiments that Dave Wineland is performing in Boulder and the one we are doing in Paris are, so to speak, mirror images of each other. In Boulder, what Dave Wineland and his team is doing is to trap single atoms. He used a set of electrodes to provide forces which trap single quantum particles, and he uses lasers to prepare these atoms in quantum state, to cool these atoms down, and to detect them. And in Paris, we do the opposite. We trap the light, not the atoms, we trap the light between mirrors, and we use a beam of atoms crossing this photon trap to prepare and detect the field. But we don't use just any kind of atom. We use special atoms, which are called Rydberg atoms, very excited atoms, which are exceedingly sensitive to microwave photons. In fact, we do this experiment with microwaves. So in our cavity experiments, the photons are detected and manipulated non-destructively by the perturbations they produce on very excited Rydberg atoms. The word destructively is very important. Usually, when you detect photons, you destroy them. The photons are transformed into photoelectrons, and so when you get a click on a photodetector, the photon is dead. And when you see something with your eyes, the photon is dead on your retina. Here we are doing much more subtle experiments in which the photon imprints an information on the atom, but is not destroyed by the process. I just show you here very briefly a picture which shows 5 beryllium ions in the trap of Dave Wyman. This is an experiment which was done about 15 years ago. And then you see 14 and then 30 calcium ions in another trap. And so you see that one is able now really to prepare strings of atoms and which interact with each other. And each of these atoms gives a bright spot because it scatters a lot of photons into the detectors. And these photons are used to see the atoms, but also to prepare them in one quantum state or in the other. And each of these atoms can be considered as a bit which stores a 0 or a 1. In fact, it's called a quantum bit because bits can be in a superposition of 0 and 1s. And if you count the number of available states, you see that if you have 30 atoms, as you have in the lower trace, the number of quantum states is 2 to the 30, to the 30th power, and 2 to the 30 is 1 billion. So you see that you have in this lower trace, which looks quite simple, 1 billion quantum states available. And not only that, you can also prepare the system in any superposition of this 1 billion quantum state. So in fact, you have a kind of atomic abacus which is being used for storing and processing quantum information. I will come back to that at the end of my talk very briefly. In our experiments, the sketch of the experiment is symbolized here. So we have 2 mirrors. In fact, these are superconducting mirrors. The surface of the mirror is coated by a very thin layer of niobium, which is superconducting at low temperature. And you see here a Rydberg atom inside, just big atom inside this cavity. So one atom interacts with the field in the cavity, which contains 0 or 1 or a few photons. What is very important is that these cavities are very, very good cavities. In fact, light can bounce more than 1 billion times on each mirror before being absorbed or scattered. And so if you unfold the trajectory of the photon going back and forth between the mirrors, you have a trajectory of about 40,000 kilometers, and the photon can stay in the cavity for about 1/10 of a second. So it's a very, very long time. If you think at this cavity, you know, if you are in an elevator which has 2 mirrors on the left and the side, and if you look, you see a reflection of your own image, but usually with such mirrors, you can see 30, 40 images because the mirrors are not very good. If you were in an elevator with this kind of mirrors, you would see more than 1 billion reflections of yourself. That is the whole population of India by reflecting only one person inside the mirror structure, which tells you how good these mirrors are. So in fact, you can keep the field for a long time. And what we do in the experiment is to send sequences of atoms one by one. Each of these atoms interact with the field, then it emerges on the other side, and we detect the atom. And from the atomic detection, we get information about the field inside the cavity, possibly without destroying the photons. I don't have time to describe the experiment, but I will just show you one result here. I cannot tell you how this was done, but the picture that you see here is a kind of abstract representation of the field in the cavity. It's called a quantum tomographic picture. And it shows 2 peaks, the left peak at the left and the peak at the right. And these 2 peaks represent 2 different classical states of the field, 2 fields which have different phases. And you see that the field that you can prepare in the cavity has the 2 phases at once. It's called a Schrödinger cat with analogy with the picture I gave you before. And so you see, you can suppose that the right peak is a live cat and the left peak is a dead cat, and the 2 states are surviving simultaneously. And in between this peak, you see fringes in this tomographic picture. These fringes are similar to the fringes you see in the Young double-slit experiment. They just express the fact that we have a quantum superposition of the two states. And I will show you a movie of what happens if you prepare this kind of cat state and let it survive in the cavity for some time. Unfortunately, the movie is not working because we went from one computer to another one, but I will describe you what happens. As a function of time, you see that the fringes are washed out. After a very short time, you don't see the fringes anymore, which means that after a short time, the cat becomes either dead or alive, but not dead and alive at the same time. So this kind of experiment, in fact, shows a decoherence in action. And we were able to show that if you increase the size of the cat by getting more and more photons into the cavity, the disappearance of the fringes becomes faster and faster. And this is an illustration of the fact that decoherence makes large systems appear classical very fast. So I don't have time to describe many experiments of this kind, but I will just give you a brief glimpse of what can be done. We can now, in fact, trap atoms in a lattice. We can prepare a lattice made of interfering laser beams and have one atom in each of the lattice sides, and you see these atoms from the light they scatter. So you see this is a two-dimensional lattice of atoms which are being studied in one lab in Germany, the lab of Immanuel Bloch in Germany. And you can study how these atoms behave on these lattices. You can also perform this kind of experiment with artificial atoms. I'll just give you two examples. Here you see four superconducting circuits which are interacting with each other. Each of these superconducting circuits behaves as a quantum object. You can define two quantum states and couple them together. And this kind of superconducting circuits are being studied in many labs. A company like Google is developing research in this field, and they are trying to entangle more and more of this system to study quantum information. Another way is to prepare artificial atoms in quantum dots to realize very small nanometric traps for electrons, and couple these quantum dots together, as I show here, also to try to realize entanglement and some quantum information processes. What are the perspectives of these quantum technologies? One very promising application will be to realize quantum, and it's already working, to realize what is called quantum simulators. You see, if you are able to prepare arrays of atoms on 1, 2, or 3 dimensions, the kind of arrays I have shown to you, you realize situations which occurs in the real world but at a different scale. This looks like a crystal or like a condensed matter structure, but in real materials, the atoms are at a few angstrom from each other. In these materials, you can realize this kind of system in which the atoms are at micrometers from each other, and they interact at a much longer time scale with smaller energies involved, and you can follow much more easily what happens. So you simulate situations which occur in the real world, but with different orders of magnitude, which make, so to speak, a slow motion of the real situation. So you can control this system, and you can simulate what happens in the real world. You can also engineer different kind of interaction between the atoms. Let me take an analogy. In fact, this looks like a chessboard. Each of these atoms can be looked as a piece in a chess game, and you know that in a chess game, the different pieces are interacting in different ways with each other, and you can do the same here. You can have different kind of atoms which interact differently with each other. But in a classical chess game, when you move a piece, you move it in only one direction. In the quantum game, you can move the pieces in a superposition of different directions, and so you have much more possibilities. Even a classical chess game has a lot of possibilities. That's what makes the game interesting. But think of how much more interesting it will be if you can move the pieces in superposition state. In a classical chess game, the number of possibilities is large, but a classical computer can keep track of a lot of them. That explains why computers beat humans now in chess. A very powerful classical computer can beat a man because, a chess player, even a master, because the number of possibilities is large, but not that large. In the quantum game, the number of possibilities becomes so huge that no classical computer can follow. And so it's impossible with a classical computer to predict all the states that you can obtain. But if you do the simulation really, you can find situations, you can find new situations, new quantum states, which can maybe one day be useful for new applications. So this kind of game gives us some guidelines to synthesize new materials. And people believe that by doing that, one day one should, for instance, be able to find superconducting materials at room temperature, which would be very interesting for applications. The last example I would like to discuss in a couple of minutes is a quantum computer. A quantum computer would really realize a kind of huge Schrödinger cat, which would be tamed to perform calculations in parallel ways, to have a kind of massive parallelism in which the computer would follow at the same time many logical passes. So how it would work and why it would be useful. What I show you here is the trend of classical computers. You see evolving over time the size of a qubit, of a practical qubit. Back in the 1960s, a qubit was a huge object which counted billions and billions of atoms. And then as time evolved, it was possible to prepare qubits smaller and smaller in size using lithographic methods, using the improvement of nanotechnologies. And now in the year 2017, we are close to the point where the qubits will have the size of a single atom. And this progress has made the computers more and more powerful. This is well known, this is called Moore's law, which tells that about every 18 months, the power of computers increase by a factor, by a very large factor. And this is, of course, coming to an end now because we cannot have smaller qubits than the size of an atom. So the only hope to go beyond that is to go from classical to quantum qubits and to add the power of state superposition to these computers. And so the quantum computer would be, as I said, a huge Schrödinger cat computing along different passes with a lot of entanglement and so on. But of course, there are a lot of difficulties along the way. Decoherence is a big problem. If you try to make a computer with large number of particles, the decoherence becomes faster and faster, and you need to control it, and you have some ideas. We have some ideas to do that. It's called quantum error correction, but it's still not enough. You need to find the right kind of candidate for the qubit. Will it be real atoms or artificial atoms is still debatable. And you have to find useful quantum algorithms. What is the sequence of operation that the computer could perform in parallel? What kind of entanglement should be realized to get interesting algorithms? So much more experimental and theoretical research is required. And when I am asked when will we have a quantum computer, I used to answer first, I am not sure we'll ever have one, and when I don't know. I just am very careful because I remember what people said 100 years ago about modern technologies. So let me conclude by a few remarks. First of all, it's hard to make predictions, especially about the future, as Niels Bohr said one day. And so it's very difficult to know where all this is leading. But there is one thing which is sure, is that if you don't do this basic science, then there will be no application. So all the application, all the innovation come from basic research, and from the development of basic research into application, you have many, many steps. You have to combine different trends of basic research together to get a given application. And the example I gave you in the past, the laser, NMR, the computers, the atomic clocks, are examples of that. The people who invented the basic ideas, who discovered the basic ideas, had no idea of the application which would come after decades of work. So the past teaches us that wonderful applications often emerge in a serendipitous way from this blue sky research. So in the field of quantum physics, what is clear is that we need to combine research in basic and applied science, and this will develop novel quantum technologies for communication, for computing, for quantum simulation, as I told you already. And this research has to be carried on at the basic level by academic institutions, universities, research institutes, and at the applied level by private companies which have to bet on future quantum technologies. And this is a stage at which, the stage at which we are now with this research. So there is a lot of hope that we are at the eve of what is called the second quantum revolution. And there will be applications, and there are already applications in the domain of communication, the domain of very precise measurements. I did not have time to discuss that, but quantum metrology is also a very active field. So I hope I gave you some kind of very general overview of this very interesting domain of research, quantum science and quantum technology, and I thank you for your attention.